Okay, Santa, we kind of got started without you, but Jose reminded me I had to, I'm supposed to be recording this. So we are on page 187, doing example 1. If any of the explanation before that eludes you, let me know in class and I will help you with it. Okay, so example 1. We're talking about absolute, but it means absolute on a range of values, like from A to B, for right now. We call them global or absolute. He's just trying to give you the vocabulary you might see in the book. We will call them absolute maximums and absolute minimums. They're the ones that are the absolute. Okay, all right. Anyway, example 1 shows a piece of a cosine curve in red and a piece of a sine curve in the same interval from negative pi halves to pi halves. And if that's where you limit those, obviously those go on forever. But if we want to just look from negative pi halves to pi halves, then the cosine curve has one absolute maximum of 1 that occurs at 0. Do you understand my words? The cosine, I'm talking about the red one.
Yeah.
Has one absolute maximum of 1 at 0. And it has 2 absolute minimums of 0 at negative pi halves and pi halves. You understand these words and where at comes in, stuff like that? The sine curve in that same interval has 1 absolute maximum at an endpoint. So did cosine, which is for the minimum. Anyway, the sine curve has an absolute maximum of 1 at pi halves, and it has an absolute minimum of negative 1 at negative pi halves, and that's how we say it. Okay? The value is the y value. At tells where it occurs on the x-axis. Okay, moving on. This next thing it's not difficult, but it can be a bit surprising if you try to discover it on your own. I want you to look at the 4 graphs on page 188 on the left side of the page. They all appear to be the same, except for some parts of it are dark blue and some parts of it are light blue, right? And in some cases, points are solid, and in other cases, points are open. So there are some differences, but they're all discussing the typical parent function mathematics, which you are extremely familiar with at this point. So take a look. The difference between from one to the next has to do with the domain and how it's defined. In the first one, it says y equals x squared is your function, and the domain is an open interval from negative infinity to infinity. You can't have a closed-end interval involving infinity. So in other words, we're considering the entire graph, and that graph has no absolute maximum. I hope that's an easy concept for you. But it has one absolute minimum of 0 at x equals 0. Yeah? That's pretty easy. All right. If we look at only this graph in the B part, we look at only this piece of graph that is in the closed interval from 0 to 2. That's the only chunk of it we want to look at. Then it has an absolute maximum of 4 at 2. And an absolute minimum of 0 at 0. That make sense? Okay. Now comes the ticklish part. If instead we look at the semi-closed interval from 0 to 2, where it's open at 0 and closed at 2, then it has an absolute maximum of 4 at 2, but it has no absolute minimum.
Why?
Because you can get as close to 0 as you would like without arriving. Yeah. So you tell me what you think the absolute minimum is, and I'll find a smaller one.
I got it.
You understand that idea?
Can I write it on the board?
Oh, brother.
All right, Professor.
Watch this.
0 raised to Google 0.
That I can prove to you is 0, which is not included.
That's not 0, there's a 1.
No. 0.
Oh.
It's a limit.
But it doesn't arrive at 0.
Yes, it does.
Yeah.
Yes, it does.
I read it on Miss J.
I'll prove it to you at another time. You missed that, Savannah. It wasn't worth saying. All right. Okay. Here we go. So you can get as close to 0 as you would like all limits are, with an open interval like that, and you can't actually arrive at 0, so there is no absolute minimum. We okay on that?
There's no way to write it.
Because there is no number that is the absolute minimum value. There's a floor to it. It is bounded. But you can't get to 0, so you can't get to the minimum value. Okay? And then D part, if you have the totally open interval from 0 to 2, there are no absolute extrema. Because you can't get to 4, and you can't get to 0. So there's no value that
Could
is
you write the
absolutely
extrema,
greater.
the extrema as a limit? Say the absolute maximum is limit is x approaches 4.
That's what I'm
No,
saying.
not with an open interval.
Why not?
You think about it for a while. It's, with the open interval, the idea is, and this is what we're gonna go with, whether you believe it or not, the idea is with an open interval that you cannot get to the endpoints of that interval. So whatever you believe the y value is that is a minimum, I will find one for you that is smaller yet.
Which is what I feel like the limit is saying, is that you can keep finding small limits.
Yes, but this is not the limit, this does not involve the limit idea.
It's not freezing.
We're trying to get closer and closer and closer, yes, and that feels like a limit. I understand where you're coming from there.
Yeah,
But the
that's
open
what's
interval says that you can get as close as you would like and still never arrive at the absolute maximum or minimum y value. You can never arrive at it.
That makes sense.
I know.
So the limit's saying you can get as close.
Yes, but you can't
But you never
find one that
arrive.
is the absolute, the minimum value that, for which there are no values less than that. Because of the open interval.
We were looking for the absolute minimum, or the minimum. We want an exact point.
Right, we want a number that we can assign it to, and we can't with an open interval. Okay. All right, I have a little star between example 2 and theorem 1. Example 2 shows that a function may fail to have a maximum or a minimum value. This cannot happen with a continuous function on a finite closed interval. Finite meaning it goes from here to here and we include the endpoints. There will always be a maximum and a minimum, absolute value, absolute maximum and minimum value on a closed interval.
How
Or
would you write
any
it
function.
with a line?
What's that? If it's a horizontal line, then your max and min just happen to be the same number, but they are both the max and the min at the same time. That's a boring type of situation, but it is a unique one. It's interesting, very interesting. Okay, so look at all these pictures then at the bottom of page 188. Capital M stands for absolute maximum, it's a y value. It's not, it's a distance, it's a y value. And little m stands for an absolute minimum. So if you're looking at this interval of this polynomial function, looks what it looks like to me anyway, from A to B, then the absolutes occur in the interval, and inside the interval, kind of like the one that poor Savannah just keeps having to stare at. I like this. They both occur inside. On the next one to the right, they both occur at the endpoints. That's possible if it's a closed interval. On the third one down, or the second line, first one there, the absolute minimum occurs at an endpoint, the maximum occurs at an interior point. It's not a big deal. And on the last one, the minimum occurs at an interior point, the maximum occurs at an endpoint. So you see all possible situations there. It's the graph at the top of page 189 that brings it all home here. Because we've not talked about locals yet. Local. A local, if you're looking on the interval from A to B, like on page 189, if you're looking at the graph from there to there, you'll notice that there's one point of non-differentiability at D. Do you see that? Because it's kind of cornery there. Yeah, cuspy. Okay.
Isn't that just
Still-
our regular max and mins? That's just what we would normally say, like, oh, that's
Yeah,
max.
yeah. Just because it's not differentiable doesn't mean it can't be a maximum or minimum. As long as it's continuous on that interval,
That
that's,
was removed. That wouldn't be maximum. If it was removed at that point, we can.
no, right. If the interval we were considering was from A to D, open at D, and then open at D and closed at B, then we could say anything about what happens at D.
We couldn't limit it then.
Nope. Okay, so you take a look at those words that they have associated on that graph. You can see the absolute maximum, why they call it that, can't you? Do you see there's also a local maximum at C? It's not as high as the one at D, but still in the neighborhood. I know it's a very strange word, but in the neighborhood of C, there is nothing higher. And you say, well, how big is the neighborhood? And the answer is as big or small as you would like. Well,
As long as.
tending towards small.
So as,
Small neighborhood. It's the maximum in a small neighborhood surrounding C.
so as long as the point on the right and the left, both slopes are moving in the opposite direction.
Yes, and we'll talk about slopes. That's an actual thing we're done. You can see they call the absolute minimum at A because there is nothing from A to B that is lower. And yet there is another local minimum at E. At C. E. No, that is E. It's going. Okay. At E, there is a local minimum because nothing in the neighborhood of E is lower. However, in the entire interval, there is a local one. you understand local and absolute? A difficult concept. Okay, and so in the definition there, if you want to read just a little bit more notation, I'm not going to spend a huge amount of time on this. It says you have a local max at C if f of C is greater than all the other y values in some open interval we call the neighborhood of C, okay? So it's really easy to identify, especially on a graph. Okay, now please look, just before it says finding extreme values, that paragraph just above it, there's something important in this too. An absolute extremum means the one that's the biggest, the absolute biggest in an interval, is also a local one because it's the biggest in its neighborhood. Okay, and the last sentence here, hence, a list of local extrema will automatically include absolute ones, if there are any.
There has to be.
No.
There doesn't have to be one if it's an open interval. Well, what we're saying is if you make a list of absolute extremes, it will always include the absolute ones. If they exist. Okay? All right, now here comes the calculus. Finally, we're getting to some calculus here. See you later, man. Theorem 2. If a function, this will make good sense to you. This is not a hard concept, and you probably already discovered it. If a function f has a local maximum value or a local minimum value, local we're talking here, at an interior point of the domain we're looking at, then its derivative exists at C and is equal to 0.
Oh.
Is that kind of a duh?
Yeah.
Moving on.
I do that.
However, and I need you to separate this in your mind, critical points are what we will look for. And critical points include not only where the derivative is equal to 0, but also where it's undefined. So, on the previous page, go back to page 189, on the previous page, listen, on this graph here, this is a critical value, the y value here is a critical value. So is this one and this one, even though the derivative is undefined, that is still a critical value, and that one. And what it does is it takes all these billions and billions of points on the graph and limits it to 1, 2, 3, 4, 5 possibilities for looking for extreme values. Critical values. Get this straight. Critical values are places, are x values to look for extreme values. Doesn't mean you'll find them, but they're the only places where they will occur, if they occur, is at critical values. And I haven't really told you about the definition of critical values, but this is it. You find the derivative of a function and you set it equal to 0, but you also ask where that derivative is undefined. So you need to find the x values where the derivative is 0, or and or undefined.
Should I find the maximum and minimum as a,
I didn't hear you, John.
don't worry about it. Like just algebraically, would we find any critical points, however we do that, I assume we're gonna talk,
Yes.
and then find the derivative to the left and right and see if it's up and down?
Yes.
That's why, that does not sound extremely fun.
Jake's just dumb.
Okay. That's all.
Not dumb, just lazy, Sam.
Okay. So listen, your first goal in doing these kinds of problems is to find the derivative of the function and find where that derivative is 0 and also undefined. Those are critical values. When you have those x values, where those things occur, where the derivative is either equal to 0 or undefined, the x values where they occur, then you find the y values that go with them in the original function and compare those for maxes and mins. So here we go with example 3. This will make much more sense when you see an example done. It says find the absolute maximum and minimum values of f of x equals x to the 2/3 on the interval, and it's very important you note, on the closed interval from -2 to 3. What that means to you, or what it should come to mean to you pretty quickly, is not only do we have to set the derivative equal to 0 and find where it's undefined, we also have to consider the endpoints. They may also be extreme because it's closed. If it were open, we wouldn't have to consider the endpoints. Only the ones we found inside. You know what I mean? Okay, so if you have a closed interval or even a semi-closed interval, you have to check the one that's inclusive. Okay, so we have a closed interval from -2 to 3. Our function is x to the 2/3. And you can see a graph of it. It's going to be really clear from the graph why we get what we get. But I want to show you the pencil paper method of doing it because it can become important to you here pretty soon. Graph is only to verify what we get. So I have f of x equals x to the 2/3 on the closed interval from -2 to 3. Okay, so we're on our search for what's your first move? Find the derivative. Very good. So I have f prime of x is going to be anyone?
2/3 x.
3 cube root.
Or x to the 1/3. We can say cube root of x if you want. Did I lose anybody there? Anybody get lost on that derivative? Because I did an awful lot of algebra in my head. And you did too. And I don't think, are you not there, Gavin?
Okay.
Okay, all right. Let me take an intermediate step. You do? Are you just saying that so I get off your back? No? You got it?
He's just slow.
So it's 2 over 3 x to the 1/3, or if you,
I may be slow, but I have a 9.
okay, so where is this expression? Where is that equal to 0?
Nowhere.
0.
Impossible.
Well, it's undefined. Never.
It is never 0 because its numerator is never 0. A fraction can only be 0 if its numerator is 0, and this one is never 0. So it is never 0. So the next question is, where is it undefined?
Where a denominator equals 0.
Equals 0, never. I'm going to say f prime equals 0, never. F prime of x is undefined. Where?
At 0.
At x equals 0.
Why does it matter that never equals 0?
What?
Because you're trying to find.
Because
it matters that
Because we're trying to find critical values, and critical values are x values for which the derivative is 0 and undefined. So I'm considering them both. And there turned out to be only one critical x. One critical x. So here's the deal, folks. This is how you finish the problem. To do it right, show your work. You would find f, not f prime, but f of -2, f of 0, and f of 3. Endpoints, critical values. Why endpoints? Because it's a closed interval. If this were an open interval at -2 and closed at 3, I would eliminate this one. Check these two. Are you with me? So we find the y values for each one of these things. Not the derivative. The derivative only gave us places to look, but now we look for them in the original. What is -2 to the 2/3? What?
Where do the endpoints have to be critical values?
Because the maximums or minimums, because you can actually arrive there when it's closed. So the endpoints may be the highest point in the place we're considering.
But what if they're not?
Then you don't write them down. We're only finding the y values for these. We're finding the endpoints and the critical value, or the critical values that we found for the x's. We're finding the y values that belong to all of them. Then we will compare those numbers and identify an absolute max and min.
Yeah, so the endpoints aren't critical point values, they're their own thing then. I assume we just consider because frequently they are the maximum.
Yeah, they're not critical values. That's right, they aren't critical, but we sought to consider them because those endpoints may be the very highest point.
Well, I mean, with that, couldn't any point be the highest point? We just check endpoints because frequently they are more frequently than, say, 1/3 x.
No, quite often endpoints are not.
Yeah.
Either one.
But so is every other point.
We just
Like,
check
why
it
do we check
because
endpoints?
there's only a slope coming out of one side of it.
So we can't find the derivative? Is that why? Because it's not checked through by the derivative, so we have to check that out as well.
Jacob.
Yeah, it's not one of the things that shows up in the critical value. However, they could still occur there.
Yeah.
So we still have to, so this is the only critical value, but we have to check the endpoints because it's closed. Because the maximum, I'm looking for maxes and mins. And they could occur at the endpoints, though they are not critical values. We still have to check there.
Yeah.
For maxes and mins.
That's all I'm confused about.
Okay.
I'm not really confused.
Okay, good.
It's more-
Somebody grab a calculator and find this for me.
-1.
The actual function, that is -2, put it in parentheses, raised to the 2/3.
Oh,
Put
should I-
-2 in parentheses.
It's 1.5.
1.5.
Give me 2 more decimals.
87.
What's f of 0?
0.
What's f of 3?
2.080.
So this is an absolute max. And this is an absolute min. And this is neither one.
Oh, okay.
Because we're comparing the numbers. So we go find the y values that belong to these places we're checking. And whichever one's biggest is our absolute max in that interval, and whatever one's smaller is our absolute min. And the other one is not. But of all the millions of points from -2 to 3 on that graph, these were the only 3 we had to check. One was critical, the other 2 were endpoints. So that gives us only 3 places to check, which is good. What?
Can we write f of 2 as a local maximum?
No. Because the neighborhood doesn't exist on the other side of it. It says on an open interval containing it. That only
Okay.
has to be an open interval containing it. The neighborhood does. So
So
no.
it can't be a local min if it's an endpoint?
It could, if it's the very smallest value that occurs in the interval,
Okay.
considering critical.
Because the absolute maximum.
So the absolute max is also a local max?
Yes.
Okay.
No. Yes.
Yes.
A list of local extrema will automatically include absolute extreme if there are.
Okay.
Okay.
But
You
there's
guys are
gotta be
getting way
another-
more hung up on this than most calculus.
Yeah, calm down. We just keep.
Well, you did say we were.
We are the stupidest.
We are-
I did not say you were the stupidest. I said no one has scored this low. That just means you're not prepared.
That means we were the stupidest.
No, it doesn't. You
Yeah, but
interpret,
Jay,
you interpret it however you want, but I did not say that.
You did
I did not say that. That is not what was in my mind. You people were not prepared.
Then you might want to just.
Okay, this will really hurt. You're not the stupidest, but you are the dumb most disappointing. It's like you're parents. I'm not gonna punish you. I'm so disappointed.
So disappointed. Well, I'm used to that.
You guys will fix it. I'm pretty sure. I'm pretty confident. Here we go, folks. Example 4.
Alright, guys.
This is where your calculator can lie to you if you let it. So don't let it. Here we go. Example 4 says find the extreme values of f of x equals 1 over the square root of 4 minus x squared. Wow. That's a pretty involved little function.
Math.
Oh, our calculators are stupid with this, huh?
Yeah. They're just not prepared. Okay, this is our function. They're asking you to find extreme values, and they do not give us any sort of an interval. So your assumption is find the extreme values where it's defined. Where is it defined?
Everywhere. Everywhere. You guys are.
Oh, yeah.
There are a lot of real numbers. You can't plug into this and get anything real.
No, you're right. Everything from -2 to 2. Yeah.
What kind of an interval?
Infinity to -2,
Um,
and then from 2 to infinity does not fit in there.
Okay, so tell me what does.
open in-
-2 to 2.
Open or closed?
Open.
Close.
Like the parentheses, not brackets.
Brackets, not parentheses.
Open or closed?
You can close. Oh, but that's undefined.
Yeah.
Open. See?
Listen. Shh. Closed if you're only considering the square root, but the square root's in the denominator. So it's open. Do you all understand why it has to be an open interval from -2 to 2? If this is anything bigger than 2 or -2, then you're taking 4 minus something bigger than 4. So that'd be negative. So it has to be from 2 to 2. But it also, if this was 2, you'd have 4 minus 4, which is 0, which you can square root, but you can't divide by it.
So it can't be 2 or
Right. Only the open interval.
-2. It has to be open because that does not.
But the range is not prepared.
1/2.
But anything up to it. 4 minus anything as close to 4 as you would like is still square rootable.
Yes, he's right.
Right up to 2 is square rootable, but it makes a 0 for a divisor. So we understand that even though they didn't give us an interval, we know that the interval is this, which means we don't have to look at the endpoints because it's open. We only have to look at the critical values for maxes and mins. Do you understand this or not?
Yes.
So what do we do to look for critical values? Find the derivative. That'll be a little. Can I rewrite this just so that we can all see it in our eyeballs here? It's going to be 4 minus x squared to the negative 1/2. I'm just writing it up here so we can see that. How do we take that derivative?
Times it by
So
the
negative 1/2.
1 over, Gavin got it. It'd be negative 2.
Negative 1/2,
Oh, yeah, Gavin's right.
Gavin's right.
Negative
Parenthesis.
4 minus 2x.
4 minus x squared,
To
To the
negative 3/2.
negative 3/2 times
2x.
Oh, stupid chain rule.
negative 2x.
Oh my goodness.
There's a lot to keep track of there. That's the chain rule right there. Did y'all see it?
Yeah.
Sonny? Sonny's forehead was wrinkled, so I was wondering if she was okay. She's going. Okay. Everybody clear on this derivative? Now, I haven't cleaned it up at all. We understand all the derivative
Is
here.
that the entire thing? What about the numerator?
One.
Yeah, where did that go?
Yeah, it's not a quotient rule. I renamed this as this. So I could use the power rule. I brought this up and named it to the negative 1/2 because it was in the denominator, now it's in the numerator.
Oh, and then you're multiplying.
Yeah, now I'm using rather than the quotient rule.
If it was like 2 over that, would you have to have a 2 in the renaming?
Yes, you'd have to have a 2 right here.
All right, we're good.
Okay, so if we clean that up, it's going to be a negative 1/2 times a negative 2, which is positive 1. So it's going to be x over, well, I'm not gonna do the radical part of it, but it's gonna be over 4 minus x squared to the negative 3, or to the 3/2. Did I mess anybody up there on that simplifying?
No.
Everybody clear?
No.
You're not clear, Jose? You're good? Okay. That thing in this form, I would like to set equal to 0. Where is this fraction equal to 0? What value of x?
0.
At x equals 0. And you have to also make sure that if it makes the numerator 0, it does not also make the denominator 0, which it doesn't. It's x over 4 to the 3/2. Where is it undefined?
At 2 and negative.
Positive negative 2.
At x, at x, come on. X equals negative 2 and 2. It is undefined, however, it's not in our domain.
So we don't.
Do not look there. We only have to look at one
That's
place.
annoying.
It is annoying.
Awesome.
How is that annoying? That's awesome.
Yeah, it eliminates the things you have to do. So all we have to do is find the value of f of x. I'm sorry, f of 0. That's the x value that's not going to work at. And what do we get when x is 0? What's the value? 1/2. Now we have to answer, and we can do that graphically. It's very easy. We have to answer, is that a max or a min? Now I want to show you how we know. I need to show you this new thing, so listen carefully. If you don't have a graph, well, actually, a graph always verifies what your conclusions are, but you have to show your conclusion using the calculus if you want to get full credit. You can't just say because the graph has a minimum there. The graph is never a definitive argument. It has to be analytic, has to be on the board. So we understand that this has the opportunity to be a max or a min. Here's what you do, folks.
Oh
You draw a number line, an x horizontal number line, and you put all of your critical values on it. And the critical value, the only one we have is 0. Then, this thing, what I'm building here is called a sign chart. Up on the top, you put f prime of x. On the bottom, you write your conclusion based on the value of what happens here. And it's not the function, it's
The derivative.
It's the derivative. We already used the function to find this y value. We're wondering if it's a max or min. We know it's a min, just listen. We use the derivative on either side of that critical value to determine whether it's a max or min on paper, not graphically. And here's how you do it. You choose a number in the region of this number line to the left of that critical value, such as -1, and you plug it in. Shh. If you plug it in, you get -1 over 4 minus 1, because we're squaring a negative, to the 3/2. Is this a positive? This is a negative number, right? And it's over that'll be 3 to the 3/2. Will that be positive or negative?
3 to the 3/2.
3 to the 3/2. Positive. So the result here, shh, I'm not interested in the actual values, only the signs. That's all I'm interested in here. When I plug -1 into the derivative, I get a negative number. right?
So our slope is negative.
You can just put a minus sign there if you want. Now choose a number in this region on the other side of a critical value. 1.
1.5.
Makes it this. Makes it this. Yeah? Did you catch that? And that's positive. Now remember, we're talking about the derivative. And kind of, sort of, this is what's going on. 0 is right here somewhere in front of my face, right in the middle of my face. See? It's a better word. 0, okay? What's happening to the left? What kind of a slope have I got?
Negative.
A negative 1. What do I have to the right of it? A positive 1. What happens right where they meet? A minimum occurs there.
And when I said that 20 minutes ago, Sam was like, Jake, you're so stupid.
I did not say it.
You
No.
did.
I
said
unprepared.
You said something totally different though.
I don't even know what you said.
I said,
Oh,
it's
I
a derivative. See if I can-
That's what I asked her. I asked her something.
In other words, folks, if the graph, this says, by the way, this is the actual interpretation of this. When the slope is negative, it's decreasing. When the slope is positive, it's increasing. Which means if it's coming down until it gets to 0 and there, right there, it begins to increase, it had to come down and go up, that's a minimum. That make sense? That is not a hard concept, but this is how you're gonna have to show it. Give me a sign chart, show me what negative and positive mean for the derivative, and then interpret what you've got. You see that?
Yep.
That's the math behind it. So you put your critical values on a number line and you plug values into the derivative to the left and to the right of your critical values and determine whether, based on whether they're negative or positive, whether it's decreasing or increasing, which allows you to conclude a max or min.
Is the derivative, are you figuring out the derivative is decreasing, increasing?
The function, that's what we say. The derivative is negative here and positive here, which means the function is decreasing and increasing. If you want to put this here, I'm sorry, that there to remind you which one's which, that's fine. But the function is coming down, the function is going up, therefore there's a minimum where it switches gears.
Yeah, he's the best one.
Okay,
He brags about it all the.
okay, listen up. Shh. Look near the bottom of page 191. Not example 5 yet, but near the bottom of page 191. Shh. You look at the pictures while I read the words. While a function's extrema can occur only at critical points and endpoints, not every critical point or endpoint signals the presence of an extreme value. It just provides a place to look. You may not find one there, but maximums and mims can only occur at criticals. Doesn't mean they will, but they're the only places to look. Listen. Shh. This figure that you're looking at illustrates this for interior points of an interval. Okay? Take a look at what we made here. You see on this graph right here, I'm talking about the first one right here, Savannah, this one right here. First one right there. Do you see how it looks like it has a slope of 0 at 0? That means that's a critical value, because if we had this function's statement, we could find its derivative, set it equal to 0, and we would find that it is 0 at 0. But that is not an extremum. Why? Because there is no sign change over that critical value.
No.
It's positive and then positive. If there is no sign change over the critical value, I'm going to use the actual symbols because that's how they use them in the book. If it doesn't go from negative to positive or positive to negative. In other words, in this region, if the derivative is positive, and then over here it's also positive, and this was a critical value because it had a derivative equal to 0,
It's just a.
then what you have is what we call a shelf point. And that's what's going on here. Because the slope of this curve to the left of 0 is positive. See, any slopes that you draw will be positive. The slopes of this curve to the right of 0, right there, they're all positive. And yet right at 0, its slope is 0. Doesn't mean there's a max or a min there, and you can tell that there isn't because there's no change in sign in the derivative, making it a shelf point. Also, if one of your critical values occurs because it was undefined, that's another place you have to look. You may, not always, but you may have a situation like the graph on the right, where right at 0, the slope is undefined because it's vertical. Got a vertical tangent there. Still, That would have been a point that shows up on your sign chart, but there would be no sign change. Because to the left of that critical value, the slope is positive. Think of a tangent line there. And to the right, it's also positive. Which means we looked at 0, but we didn't find one because there was no sign change indicating a max or a min. Do you understand this?
Yeah.
Look for the sign changes over those critical values. If they don't occur, then it is not a max or a min. Just a place to look. Yes.
What happens if it's like one of those that just barely dips down?
It will show up as a 0, and to the left and to the right.
Oh, we'd actually get two critical values though, right?
Yeah.
Oh, okay.
Yeah.
Never mind. Because you'd have.
And you have to check in between them. So if it is a very, very small region, you
Critical
have to find one in between the whole time.
Okay. Critical value.
Yeah, yeah.
So you have two really.
Those are good questions. Okay, 2 more examples, folks. Actually, the reading of example 5, the presentation of problems on page 191. Let's see if we can figure it out without turning the page. Example 5 says, find the extreme values of, and oops, now we've got a piecewise.
Juicy.
By the way,
So we just.
by definition on a piecewise function, a place to look, it's not a critical value because it doesn't fit the definition, but another place to look besides the endpoints if it's closed is the place where one function breaks from one to the other. You have to look there for possible maxes and mins as well. Corners, cusps, discontinuities, wherever the piecewise function breaks from one function to the next, that x value is also a place to look. So what is this? What's the first function?
5 minus 2x squared. X is less than or equal to 1. And then it's x plus 2. When x is greater, yeah.
Okay. What is the derivative of this function?
Do you find the derivative of u?
Yes.
Okay.
And it's still at these boundaries. It still happens that they switch places in this x. It stays that way. What's this derivative?
Negative 4x.
What's this one's derivative?
1.
When is this function's, if we set this thing equal to 0, when is it equal to 0? When x is 0.
Yeah.
Okay. Does x equal 0 fit in the range of values where this one's defined?
Yes.
Yes. If it didn't, then it wouldn't matter. So, f prime of x is equal to 0 at x equals 0. Where is it undefined, the derivative?
Definitely a 1. X.
It might be undefined at 1. That's something we would have to consider.
Well, undefined.
Is it undefined at 1,
Oh,
the derivative?
no. Wait. Oh, no. Undefined. No. But it's indirect.
Actually, it is, but it's really hard to tell from this. What I'm saying is, shh. Wherever this derivative is equal to 0 is a critical value, and also the point where it changes from one function to the next, that 1 right there is also a place to look. It's not a critical value. But when we go to set up the sign chart, we will put on a 0 and a 1. We'll have both of them. Okay, so f prime at 0, f prime of x in this region here. We're only allowed to look on the graph where this region is defined for, where its domain is. So if we put -1 in, which one are we going to put it into? The top one, but we're doing the derivative here. So if I put -1 in right here, what will its value be? Positive or negative? Positive. Okay. Between 0 and 1, which one of these are we going to look in? Here. Pick a number between 0 and 1.
0.5.
What?
1/2.
A half.
0.5.
-4 times a half. Positive or negative?
Negative.
Negative.
Would you be quiet?
No, because it
Yeah,
includes,
but it includes it.
it includes it, and we're looking for it.
Fine, you'll still get a negative.
Okay.
I would choose something in between to be safe.
And then 1 and 0.
Okay? Now, anything after 1, we're only allowed to look where?
0.
Here. What's after or in the region from 1 up? The slope.
0. Positive. 0.
The slope.
1. Yeah, 1.
which is
Positive.
positive. Guess what that means? We have a,
Oh, positive and negative.
oh, I like positive, yeah, positive then negative. We have what at 0?
A
A
maximum.
maximum.
Then a minimum.
At 1, we have a minimum.
Does that count as a minimum?
Betcha it does, because there's a change in sign. It would be wise of you to make sure that this is continuous at 1. When x is actually 1, this is 3, isn't it? The y value is 3 on the actual function. When x is 1 here, and I know you're not allowed to put 1 in, but right there close to 1, it's also 3. So it is continuous there. But it's got a problem. Switching from one to the other, it's got a cusp or a corner. But still, because the sign changed this way, negative to positive, we have a minimum there if it's continuous, and it was. Now, if you look at the graph, turn the page, it's very clear from the graph that we have a max at 0 and a min at 1. Locals. You okay with that, everybody?
Yeah. Yes.
Okay,
There wouldn't be absolute extreme on this graph, I think.
because they didn't give us a closed interval to look.
Right.
All right, so example 6, last one. This one's kind of interesting, and it's unfortunate that the graph is staring you at the face. However, the graph is telling you a lot, so don't suffer for it. Wow, look at example 6. It says find the extreme values of, find the extreme values of log absolute x over 1 plus x squared between. All right, so we've got quite the function here that we're going to have to deal with. It is the natural log of x over 1 plus x squared. Okay, let's see what you can remember here. What is the first thing we got to do? First of all, did they give us a closed interval to look at this on?
No.
There's nothing there, so we're gonna have to think about that. What's the derivative?
One over u. Oh, yes. So it'd be x.
Absolute value.
Why did I do that?
Because the whole thing's an absolute value.
No, because the denominator can never be 0. So I don't need absolutes on. I mean, can never be negative.
Yeah.
The denominator can never be negative.
That's what I'm saying, like the whole, the top
But
part
the
is
x could.
absolute value.
So I left it there. So it's 1 over u.
Wait, that's the natural log one?
Yeah.
Time.
1 over u
Oh,
times the derivative of that.
Quotient rule. There's no quotient
First.
What?
That's all the derivative of natural log is.
Yeah, 1 over
One
u.
plus x squared minus.
Wait a minute.
How do I get 2x?
Bottom times the derivative of the top minus the top times the derivative of the bottom, 2x over.
Over. 1 plus x squared.
All of that squared.
Now, this could possibly be negative, but I'm going to drop the absolute value from right now. The only reason I put those on there is to remind you you can't log a negative. I'm going to keep that in mind as I go, but I don't want to deal with this garbage algebraically. So I'm going to take it off of here. But I'll remember that x has to be a positive value. Okay, so now what?
Yes.
1 plus x squared over x. I'm just flipping that one
Let's
over
get rid of the 1 plus x squared.
in just a minute. 1 plus x squared minus 2x squared, which is 1 minus x squared, yeah?
Yeah.
1 plus x squared, and you're right. We'll lose one of these. Y'all clear?
Yep.
We'll lose that and one of these. So we're now down to 1 minus x squared over x
Plus x
times 1, yeah, okay, x plus x cubed. All right, I'll do that, x plus x cubed in the distribution. Okay, so that's about as simple as our derivative's gonna get. We wanna do what now?
Absolute value.
We wanna find out where's 0 and undefined. I'm gonna consider the 0 first. Where is a fraction equal to 0?
Numerator.
Wait.
Where its numerator is equal to zero.
One.
What?
Can we simplify it one?
No,
I think we can.
no,
I don't think we can.
So because you make the top negative, no, from the negative, no, that you can't do that.
No.
Oh, yeah, take a negative out of it.
No.
Stop.
Right where you're.
Stop.
Sam,
If you take a negative out, you get x squared minus one, which is still not gonna help because there's no negative
No,
down.
no, no, take a negative out of the
No.
top.
No.
Okay.
But it's X.
When is this thing gonna be equal to zero?
But you
One.
can't.
One and negative
Yeah, but
one, but x
why?
can't be negative, remember?
It's not, it actually makes it harder, I think.
No.
To flip around the order.
No.
It is zero at x equals one. Now, when x is one, does it also make the denominator zero? You have to check that out. No, so we're okay. At x equals one. You understand why negative one is not a consideration?
Yeah.
Because we dropped the absolutes, but we're under the impression that x could never be negative.
Oh.
Oh, wait a minute. If the absolute value is here, then x could be negative. It could be negative because this is forcing what we're logging to be positive, but the value of x could be negative and then we'll have absolute value. So it could be either one.
I was just thinking it was like if it's negative one, the denominator equals zero.
Denominator is not equal to zero when it's one or negative one.
Negative one.
Negative one minus one. Negative two. Okay, where is this thing undefined? At zero? Is that the only place?
Yeah.
Is that the only place where x equals x cubed?
I don't think so.
Yeah.
Okay, what? Or x equals x cubed.
Oh, negative one, no.
We already have that, and so we already have a plus or minus one business there. That's where the denominator could be zero, but we've already got that listed as a critical value. So the only other critical one is zero, is that right? Put those on a number line. We've got 1, 2, 3, 4 regions to check.
Doesn't that mean that one negative one would make it undefined and not zero?
Is it? If I
I feel
have
like
one,
we had that.
no. This should have been like this. So it doesn't produce any. The denominator's never, it's only on the, I'm sorry, the denominator is zero only when x is zero. Because of the plus sign. I was thinking it was minus. Sorry, Connor, you're right.
Right there.
So we have 3 critical values, 2 where it's 0 and 1 where it's undefined, and we have them on a sign chart up there. So let's evaluate the derivative for positive and negative. It's all we have to look for. We don't have to actually find values. So choose a value below -1, -2,
Yeah, sure.
yeah? In the derivative, that's this one right here. If I have a -2 here, what will the value of the numerator be, positive or negative? Negative. You guys that are not paying attention, at least stop talking. What's the denominator, positive or negative, when x is -2?
Negative.
-2,
Oh, the denominator.
-8.
Negative. Yeah, it's negative 10. Yeah, no, but it'd be positive.
negative over negative is negative.
So it is increasing here, because negative over negative is positive. In the interval from -1 to 0, let's try -1/2. Will this be positive or negative if the value I'm plugging in is -1/2?
Positive.
Positive, because it'll be 1 minus a fourth, right? Will the denominator be positive or negative? That's a little tougher. That's going to be -1/2 minus an 8. When it's 1/2, this is still positive and this is positive. Oops. And if we choose something greater than 1 like 2, will this be positive or negative? Negative over positive. So where do we have maxes and mins?
We have
Is this a max or a min?
maximum.
That's a minimum.
That's a minimum.
Oh, it is a maximum.
Increasing to
It's
decreasing.
a
It's a maximum.
Maximum.
Is this a max or a min? I'm gonna put this in, well, I'm gonna put a question mark here, because it's not. Stop and don't leave. What is this one?
Don't leave.
Why is this not a minimum?
It is because you cannot log a
Can't
zero.
log a zero.
Haha, we're kidding.
Well, you're right, but what that means is 0 was never in the domain of this function, never. It's not in the domain, it has no opportunity to be max or min if it's not even in the domain. And look at your graph, it lies. It looks for all the world like that's a minimum. You say, yeah, that's what I got with my sign chart too, it must be a minimum. It is not. This is an asymptote. You can't tell. Your calculator wants you to believe that's a minimum. It's not. Don't sucker for it. There is no 0 in the domain of the function, so it cannot possibly be a max or min. Consider the domain. You cannot log 0. The graph of a log curve looks like this, and it's asymptotic. It's never 0. Not in the domain. So you must consider that also. Oh, that was a fight. All right, there you go.
No, actually, the answer.
Never zero.
I don't think I'll ever get it.